Okay, are we ready to go? This is the whole crowd today? Okay. Well, last time we got to a rather startling discovery made by Maxwell. And I told you that Maxwell had first discovered that there was a term missing in these equations that he was working out for electricity and magnetism. And I reminded you that Faraday, a long time earlier, had discovered that if you have a changing magnetic field, that can create a current, a circular current in a wire, right, around a loop. So it creates what's driving that current is an electric field. So basically what Faraday had discovered was that a changing magnetic field causes a circular electric field around that changing magnetic field. Well, Maxwell discovered that it had to work the other way around, too. That a changing electric field would cause a circulating magnetic field around it. Just like we already knew that if you have a current through a wire, it causes that kind of circulating magnetic field around the wire, right? Well, Maxwell has discovered that if you have a changing electric field, it has the exact same effect, that it creates that same kind of circulating magnetic field. But the combination of the two effects, the one that Faraday discovered and the new one that Maxwell has discovered, gave rise to a whole new phenomenon that Maxwell worked out. That if a changing magnetic field causes an electric field, and then a changing electric field causes a magnetic field, that you can have, what that will produce is a propagating electromagnetic wave. That's what Maxwell figured out. Because if you start out with some electric charge that you then oscillate up and down, say, you will cause a magnetic field that goes, say, into and out of the board, and an E field that goes up and down. And that will continue, those fields will just continue to propagate outward. And Maxwell could figure out, he could actually write an equation for these oscillating, the oscillating magnetic field and the oscillating electric field. And the constants that showed up in those equations are just the familiar electric and magnetic constants that we've already talked about. You know, the ones that in Coulomb's law, there was a constant that showed up that just characterized the strength of the electric force. Well, in Ampere's law that described the force between, the magnetic fields generated by currents, there was a constant that showed up in that equation that just described, how strong the magnetic field around a current was. Well, that electric constant and that magnetic constant show up in these equations of Maxwell. And it turns out they determine the speed of the propagation of these oscillating magnetic and electric fields. And I told you at the end last time that Maxwell was able to work out all the math, and the equation he came up with relating the speed of this electromagnetic wave to those electric and magnetic constants was, I'll just refresh your memory on the mathematics. Let me see, for the electric field due to just a static charge, okay, Coulomb had let's see. We had this equation. The electric field is just equal to this electric constant multiplied by the charge divided by the square of the distance away from the charge. For the magnetic field, I gave you an equation. Magnetic field generated by a current I through a wire, a long straight wire, follows an equation like this, where you have some magnetic constant, and the magnetic field generated by that long current through that long straight wire is just proportional to the current and inversely proportional to the distance from the wire. Well, Maxwell goes through all this complicated math that I'm not going to show you, and because it's all differential equations, which you'll get to in a few years. And he comes up with a speed, let's call it, just conventionally it's called c. So that equals the speed of the wave. And the equation he comes up with is the speed is equal to the square root of 2 times the electric constant divided by the magnetic constant. And I gave you these numbers last time. This is all just review. Let me see. I think this one was 9 times 10 to the 9th, and the magnetic constant was 2 times 10 to the negative 7th. These are in units where you use meters and seconds. So, lo and behold, you work this out, and you get 300,000 kilometers per second, or converting units, the familiar number 186,000 miles per second, which astoundingly comes out to be exactly the speed of light that we already know from previous experiments, right? Remember Louis Fizeau had measured a speed of light of around 190,000 miles per second. And Maxwell just gets this number popping out of his mathematics when he hasn't put in to this calculation anything about light, right? I mean, this is all he's got is the equations of electricity and magnetism, and those equations imply, his understanding now of electricity and magnetism, since he knows that if you jiggle a charge, okay, you're going to get these oscillating E and B fields, and then he can work out the math to figure out how fast this wave has to propagate, and it turns out just to depend on the strength of the electric force and the strength of the magnetic force, and out pops this number that says that it has to travel exactly at the known speed of light. Now, obviously, Maxwell concludes from this, well, this is what light is. Okay? It's an electromagnetic wave. Now, the day that Maxwell completed this calculation, he had a date lined up for that night. And so he's going out with this girl, and during the date, they're taking an evening walk, and she mentions something about how beautiful the stars are, and Maxwell asked her, well, would it impress you to know that you're out on a date with the only man in the world who knows what starlight is? And he explained it to her, that it was an electromagnetic wave, and evidently she was very impressed because she married him. It turns out I'm not saying that the only reason for guys to learn physics is to pick up girls, but you can add that to the list of reasons. Okay. Now, this amazing conclusion has come out of the mathematics, but we would like to actually see some more experimental evidence for it, right? Well, eventually, after Maxwell, another guy figured out how to do that, and I want to tell you about his experiments. But before I get to the specifics of his experiments, let's just think about this whole idea of light being an electromagnetic wave and how we might try to go about proving that. What do we know about light? Let's start by making a list of properties of light. Well, yeah, that first section you can just call like review from last time. Maxwell's discovery of that light is an electromagnetic wave. And now we want to examine that idea of Maxwell's and first review the properties of light and then see whether we can relate them to these electromagnetic waves that Maxwell has discovered. So let's start by reviewing properties of light. Now, what do we know about light? Let's what's the earliest? Do you remember the earliest law of light that was discovered? This goes. I think I mentioned that Euclid, for example, knew this. There's one law of light that the ancient Greeks actually knew.
The law of refraction?
Refraction? Actually, I didn't know the law of refraction. That's right. But there's another law of something. Reflection. Okay, so the first law of light that people figured out was the law of reflection, which just says that if you bounce something off of a surface that reflects light, the If you have, say, call this the angle of incidence, okay, that's theta sub I, and the light bounces off this mirror call this angle that it bounces off at the theta sub r, the reflected angle. What's the relationship between theta sub I and theta sub r? They're the same. They're equal. That's the law of reflection. Very easy law, right? Whatever angle the light comes in at, that's the angle it bounces off at. Okay, now, like I said, the Greeks knew that one. Euclid knew that. Now, the second law that people discovered about light, law of refraction. And, just to test your history here, give me a year for this, roughly. Doesn't have to be an exact year, but get the general time period right. Hmm?
So can we say century?
Yeah, century would be good. Hmm?
Is it BC?
Oh, no, it's not.
No, it's not BC.
It's, I mean, people started to, I mean, remember what refraction is. It's how light bends when it goes into a material, right? And, well, first, what is the law? Does, I mean, I'm going to, here, let's say that, oh, I don't know, this is a piece of glass here. It's air up here. Here's the vertical to the surface. We've got
Was it solid glass or just a sheet of glass?
solid glass. Here's the angle of incidence. The light bends at the surface when it goes in. Here's the angle of refraction here. What's the, let's say that we characterize this glass here by some number n. Do you remember that? It's just dependent on the material, just some constant that depends on the material. What's the law of refraction? Does anybody remember? Daniel.
Okay, I might embarrass myself. Theta I is equal to n times the theta r.
Oh, that's exactly what Ptolemy thought, except he was wrong. That's the way. That's the way Ptolemy thought that refraction should work. You know, they started out with this simple law of reflection, where the angles were the equal. Okay, and then Ptolemy thought, well, the next simplest law should work for refraction, that the ratio of these two angles, I mean, instead of the angles being equal, obviously they're different in this case, but there should just be a constant ratio. In other words, the ratio of the angles should be equal to a constant. So that's exactly what you just said. Turns out to be wrong. Troy.
Theta sub I equals 1/2 theta sub R. I can't think of its times on it, by the way.
You're thinking of something else anyway. So nobody remembers this. Remember that the sine law of refraction. It's the sines of these two angles that are related. The law of refraction says, in this case, that sine of the angle of incidence equals n times sine of the refracted angle. Now, if I'll do the more general law here. Let's say, for air, this number n that applies to air is pretty close to 1, so I've ignored it. But if you had water here, say water going into glass,
How would you do that
then you would have, how would you do it?
as far as experimenting?
Oh, you could just have a big container where you had glass on the bottom and water on the top. So, yeah, Ptolemy actually did that. So in general, if you had this material up here being, say, N1, and this material being N2, then the more general equation is this. Okay, so this was discovered in the 1620s. So who else was working in the 1620s? Galileo, right. So this is, Galileo didn't discover this. Another guy named Snell did. Right, they were contemporaries. Okay, now, name something else that we know about light. Yes?
It has colors.
Yeah, okay. You can take white light and refract it through a prism, and the various colors that are in the white light bend at slightly different angles, and so you get a color spectrum spread out. Let me see. What are those different colors? What is the property that scientists can quantify that is different, say, about red light and blue light? Sorry.
Well, blue light bends more than red light.
Yeah, it does. But Newton and then later Thomas Young actually came up with a theory of light that exactly what was varying as you go through that spectrum from red to blue. It was the X of the light.
Different wavelengths.
Yeah, the wavelength of the light, right. So what Young proved that light was a wave. Okay, so let's write that down. Now, what does that mean? That how did he prove that? That light. Remember that the essence of his experimental proof was that you could take two light beams and combine them, and they could add or subtract, right? So destructive or constructive interference, exactly like water waves do, for instance. So right underneath here, it can, let me see, well, say combining waves can add or subtract in other words, light exhibits interference. Okay, so that's called, in other words, when waves combine, they can combine in phase or out of phase and add or subtract, and that's called interference. Okay, what else do we know about what do we know about these light waves?
It's a particle? Or light is a transverse wave?
Transverse, exactly. That's exactly what I was looking for. We know that scientists knew that waves come in these two different kinds, longitudinal and transverse. And shortly after they figured out that light was a wave, they figured out that it was a transverse wave. Now, what does that mean? Well, how did they figure that out? Nick?
They used the polarized.
Right. So, I mean, they figured out that light came in these two different types, because when you put it through certain crystals, if you turn them 90 degrees in different orientations, no light would get through. But if you put them in the same orientation, the light would get through. So, light can be polarized. Okay, so that's just a review of stuff that we already know, but it's useful because remember, what we would like is experimental proof of Maxwell's idea that light is an electromagnetic wave. So one way you could have really convincing proof is if you could take electric charges, basically, and shake them up and down, create something that you know is an electromagnetic wave, show that it has all these properties, okay? All the same properties that light has. Okay, that it reflects just like light does. It refracts like light does. If you have two such electromagnetic waves, they interfere just the way light does. And furthermore, that you can use polarizers that transmit the light or block it depending on the orientation of the polarizers, proving that it's a transverse wave. So if these electromagnetic waves, oh, and I should add a very important one, the speed of wave equals this familiar number. So if you can prove 186,000 miles per second. If you can prove that electromagnetic waves have all these properties, then no one in their right mind could doubt that electromagnetic waves are light, right? Okay, there was a guy who did that. And his name was Heinrich Hertz. Okay, so and Hertz had studied Maxwell's theory, and he knew of Maxwell's connection between electromagnetic waves and light. But no one experimentally had figured out, how to approach this. I mean, Maxwell had offered this brilliant mathematical proof, but it would be nice to actually demonstrate how you can generate electromagnetic waves and show they had all the properties of light. And no one had figured out how to do that until Hertz finally did it in the late 1880s. And I think he first published this, experimental proof that EM waves are light. I think he first published that in 1889. Now, Hertz is, it was known that the light waves that we're familiar with, the visible part of the spectrum, the part that Thomas Young used in doing his experiments. Do you remember what those wavelengths were? What Young discovered as the wavelength range of visible light? Anybody? It was, remember, I think I told you that, for visible light, red has a wavelength of about, say, 670 nanometers. You know what a nanometer is? Nanometer is a billionth of a meter. Okay, so really, really small. Blue was down around, well, if I go to the extreme red end of the spectrum where we can just barely see it, Okay, this is 690. And the extreme blue portion of the violet portion of the spectrum is down at 430 nanometers. So this is the range that we can actually see in. We see these light waves with these really incredibly short wavelengths. Yes?
What is white light? Like, what's it
Oh, white light is
listing out?
is everything from red to blue, right? It's just a mixture of all the colors. So all the rest of the colors are between these two wavelengths. So white light would be light that is a mixture of wavelengths that go from the shortest of 430 up to 690 nanometers. When you have all the wavelengths between these two numbers all mixed together, that's what we see as white light. If you just pick out, say, a little, you know, the portion of that light that is down around, 450, we see that as blue. The portion of that light that's up at this end of the spectrum we see as red, and then yellow, green, and so on would fall in between. Okay, so these are really, really short wavelengths. That's the only wavelengths that our eyes respond to. So that's the only, those are the only electromagnetic waves that we can see. But Hertz, in his lab, he's going to generate a very, very different kind of electromagnetic wave. One with a, where the charges oscillate slower and the wavelengths are much, much bigger. Hertz generated electromagnetic waves with wavelengths that were, a few feet long, instead of visible light, which is less than a millionth of a meter long. So but he's going to show that those waves, even though they're different from the visible light that we see, they're different in wavelength, they're much, much longer wavelengths, they have all the same properties of light that we're familiar with. Okay, now how does he do that? Well, let me give myself a little more room here. I'll fill in the details of this experiment for you a little later, but let's just start out with the just the essence of the idea. Hertz is going to start charges oscillating basically in an antenna. Okay, he's going to take a wire, actually with a gap in it. He had little metal balls on each end. And he is going to use in another circuit. Let me see. Well, that's a complication. Well, I'm going to tell you later about exactly how he got this thing started, these charges oscillating, but here, he does get them oscillating. Okay, so let's just if you accept that for the moment, he's going to get electric charges to fly back and forth along this, this metal wire that he has. And he can tell when he gets them oscillating because charges will then build up on these little endpoints and he'll see sparks in this little gap that he has in his wire. Okay. Now, this should cause an electromagnetic wave, right? I mean, this is just what I talked about before. Maxwell realized that if you jiggle electric charges, those oscillating charges will cause the oscillating fields that gives rise to this wave. And that's exactly what Hertz does. First, he generates. He starts these charges oscillating. Now, how can he detect them? Well, if he has a little wire loop, okay, with a little short gap in it, that he can stand off at some distance. Okay, now, if he holds his wire loop along the direction of the oscillating E field, say the electric field will oscillate in the same direction that the charges in this antenna oscillate. Okay, so if he stands out back here and holds his little wire loop with a gap in it horizontally, and he's got a oscillating electric field that is hitting that wire loop, that will cause the charges in his wire loop to oscillate, right? And he'll see little sparks in the gap. That's exactly what he sees. Okay, he can stand back from the oscillating charges in his electric wave generator here and detect that oscillating electric field with what he called a spark gap detector. That when that oscillating electric field hits his little spark gap detector, he sees little sparks. So spark gap detector. So he's got this is just some handle. Oscillating E wave causes sparks. Okay, so that's about all we have time for this morning, but I'll pick up what Hertz is able to do with this kind of a setup this afternoon and show you that he can bounce this electromagnetic wave that he's generating off of mirrors and show that it reflects the way light does. He can cause it to go through certain materials and show that it bends the way that light does. He can use polarizers to show it's a transverse wave. He can figure out the speed, show that it goes at the speed of light. So he's he really comes up with a very, very convincing experimental proof that Maxwell was right. And we'll see more about that this afternoon.